till now is that we have derived the Navier-Stokes equation. These are the three uh, Navier-Stokes equation. These are actually momentum conservation equations in uh, the three coordinates of the three Cartesian directions x, y, and z. Now, what we can do is that we can find some exact solutions of uh, Navier-Stokes equations, right? So, exact solutions. First, what we have is uh, known as the Couette flow. These are two parallel plates. The most general version would be a inclined plane, right? Uh, Let this inclination be theta. This would be g. So this and this will be the two components, right? This and this. If this is theta, then the perpendicular of this line is this. The perpendiculars will also have the angle theta. G cos theta, G sin theta. Also, if this is theta and this is the distance, let's say d in this is the elevation, let's say h. This is, let's say, L. In the x direction, we'll take this as x direction. Then hold on, this is theta, this is L, right? Then sin theta is h by L, right? Uh, we can write Navier-Stokes equation. We'll have these are three Navier-Stokes equations. We'll also have body force in the x direction, force in the y direction, plus some body force in the z direction, right? In the x direction, the body force would be g sin theta, right? Which can be written as g into h divided by L, right? Now we know piezometry here is equals to P plus rho gh, right? And if these are very small, uh, this tends to 0 and this tends to 0, we can write g is dh by dx. So we can write piezometric here is equals to partial derivatives, actually these are dp by dx plus rho g dh by dx. So in this equation we can combine these two, right? So fb will be minus because it is in this direction, whereas x is in this direction, minus g dh by dx. These two can be clubbed and we can write this p as p star, right? Okay, so from now on, even if this pipeline, this parallel plates are inclined, and if we consider body force, then also we can, you know, just write p star in place of p in this equation, right? Now the Couette flow in the most general form. Uh, Let me remove all these things. We will ignore body force, right? Like how I had told, the reason I've told. Just let me get rid of these parts. Okay, now uh, what we can do is that uh, we will derive this for a general Couette flow. In Couette flow, these are the two plates where the upper plate moves with a velocity of u0, flat plates, and sorry, this would be the velocity profile, right? We consider that there is a pressure gradient dp by dx which is negative. Now few assumptions: incompressible. Why? Because this Navier-Stokes equation in this form is itself incompressible, right? Steady. Once we write steady, these terms vanishes, right? This plate is very long in these directions, right? The width is huge, so there will be no change along the z direction. This is z direction, x, y, and z, right? So d by dz will be 0. Also, this means that there will be no velocity in the z direction. So w will also be 0. So this entire this thing goes right. This goes away because of there is no variation in the direction, right? V is also equals to 0. Now how V is 0? This will come from continuity equation. Du by dx plus dv by dy is equals to 0, right? Now du by dx is 0 because we can call this a fully developed flow and u does not change with x. U is not a function of x. So v is not a function of y from here. V is 0 at y equals to 0. Therefore, we can say that v is 0 at all y, right? So this term vanishes. Now from here dp by dy equals to 0, which means p is not a function of y. P is a function of x only, right? So we can write this as dp dx, ordinary derivative, right? W0, V0, fully developed, again this is 0, right? Fully developed, this is 0. So we are left with this term and this term. So the equation becomes one by rho dp, not this d, equals to mu d square u by dy square, right? Now p is a function of x only, u is a function of y only, so these two should be equal to a constant, right? We know mu, which is the kinematic viscosity, is mu by rho, so we can write it as d square u by dy square equals to mu, sorry, 1 by mu dp by dx. Now we will integrate both sides. With respect to y, we get du by dy equals to 1 by mu dp by dx into y plus c1 du by, sorry, so u is equals to 1 by mu dp by dx y square by 2 plus c1y plus c2, right? So from the boundary conditions we can find the value of c1 and c2.